Okay. How y'all doing today? All right. So I'm a little depressed today because I think I'm starting to feel as if there's just not a way we can reach the end of this class. I'm going to try. It's going to be a sprint to the finish here. We'll see. We only have what, 3 classes left? Is that right? 3 classes. That's it. Just roughly 6 hours. So, all right, let's get through 13.5. Last time we were talking about curl. We talked about how it tells you about the kind of twist that you have of a particle moving through some fluid or something like that. And we finally finished saying that the curl is a way that you can check to see whether or not a vector field is conservative. That's where we finished. So if the curl of a vector field is the 0 vector, then we know it's a conservative vector field. Also, any points within your space where your curl calculates to be 0 would mean that you are irrotational at that point. All right, so now we talk about this second operation on vector fields called divergence. And so it's a new concept, and it has a really cool visual meaning. So first, let's figure out what it is that you have to do to calculate the divergence of a vector field. So given a vector field, the divergence of F is defined to be the following. We notate it with div in front of the vector field F. So div F. And all it is the partial of the first component of the vector field, the partial derivative of that with respect to X, added to the partial of the Q component with respect to Y, and then add that to the partial of the third component with respect to Z. And your answer will be a scalar or a number. That's different than the curl. The curl, when you compute the curl of a vector field, you get a vector. When you compute the div of a vector field, you get a scalar. So sometimes we can write the div of F with some different notation. All it is the gradient vector, which we defined last time, dotted with the vector field. So if we define the gradient to be just the partial with respect to X, Y, and Z respectively, then if we dot that vector, I'm going to write it down here. If we were to take this and dot it with this field, then what you're doing is the partial with respect to X, partial with respect to Y, partial with respect to Z, and you're dotting that with the field P, Q, R. And when you do dot products, you're supposed to do this times this. Now it's not actually multiplication that we're doing here. We are taking the partial of P with respect to X. So it's not quite a dot product in the sense that we're not multiplying, but the notation makes sense. You do that, and that is what this is up here. So let's start with just a let's start with an example that we can calculate. So here's a vector field. Find the divergence of the vector field at the point 2, 1, 0, and then we'll talk about what it means. So if I want to compute the div of this, I'm going to take the gradient and dot it with x squared yz, xy squared z, and xyz squared. So when we do this, here to here, we're taking the partial of this with respect to X, which is just 2xyz. And then here to here, we're doing the partial of this with respect to Y, which gives us 2xyz again. And notice we're adding in between these. And then here to here, we do the partial of that with respect to Z, and we get 2xyz. Add all those together, we get 6xyz. That is the div of the vector field. So if we wanted to find the div of the vector field at the point 2, 1, 0, then all we do is replace X with 2, Y with 1, Z with 0, Well, that's just going to give a 0. So the div would be 0. And it's a number, not a vector. So what do y'all think? Compared to curl, isn't div a lot easier to do? Like curl, you have to do like cross product, and it's a little more computationally, but with the div, it's pretty straightforward. Now, what does div represent, right? So what we know, curl gives us like this twisting, right, within the field, but the div represents something completely different. So if the vector field represents the velocity field of a flowing fluid, then the divergence measures the tendency of the fluid to diverge or leave a point in the fluid. So when you're looking at a point within a fluid, imagine everything's in motion, right? The fluid's flowing around. We already talked about how you might have a twisting motion as you're moving. The div calculates the tendency of fluid points around where you are to be moving away or moving towards that point. I'm going to animate this with something visually. You'll see it in a second. But before I can do that, I'm going to tell you that if you calculate the div and it comes out to be a positive number, then that means we will call that the region around that point the source, which means that things are emanating from that point. It's a source. So you almost think about it like heat. It's almost like heat is coming from that point. Something is coming off it, coming out of it. If the div is a negative number at that point, then we call it a sink. And that's because things are almost like getting sucked into the point. And then if your div is 0, then we will call the region around that point incompressible. And that means things aren't wanting to move away and they're not wanting to move in. They're just wanting to stay where they are. And when you think about something like that, it's not compressible. If you could compress something, things are going to move in, right? So now we get to look at it visually. So remember, a three-dimensional vector field means that at every point in the vector field, you have a vector at every single point. So take a look at this three-dimensional graph, or this three-dimensional graph. And do y'all see, now try and imagine that there's a vector field everywhere. Okay, so there's all these vectors pointing everywhere. That's your original vector field. And I'm sitting here at this one particular point. I hope y'all can all see that point, okay? All right, there it is, sitting there in space. And I'm having the computer for this example, I'm having the computer calculate. Oh shit, I've lost my orientation here. There. I'm having the computer calculate the div. And right now for this example, the div here is 6, which means this is a source point. So how can I visually represent that? How can I get you to understand what's happening? So imagine that we can, well, let's zoom in on that ball, okay? Or that we're acting like it's a point, okay? It's actually a point. We're going to zoom in on it, okay? So we imagine it's like this little tiny point, but we're going to zoom in, right? We're going to zoom in so that it looks almost like a ball. So we know a single point doesn't look like a ball, but imagine taking a single point and making this little infinitesimally small ball around the point. That's what we're looking at, this little infinitesimal sphere. At every point on that little tiny sphere, there is a vector from the vector field, right? So if I go and I look at this, at every single little point on this sphere, there is some vector, 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 right? There's from the vector field itself. What if I could somehow measure how many of those vectors are pointing away from the sphere versus pointing into the sphere? So let me give you that visualization right now. Okay, so I've actually had the computer pick a few random points on the sphere, and any vector that's green is coming out of the ball, and any vector that's red is going into the ball and punching through the other side. Can you all see that from this picture, kind of? Doesn't it appear that we have more green coming out than red going in? Does that appear that way to you? Maybe I need to illustrate this a little bit better. This red one starts here at this point, punches into the ball. So it's going into the ball, and then it, of course, comes out the other side. The green ones, which I don't have a green pen, so I'll do it in blue. This green vector never punches into the ball. It always is moving away from the ball, so it doesn't point in towards it. Do you see the difference between the red and the green? No questions there? So if I ask the computer to give me more vectors, that was just a few, but if I ask it to do more, and more 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 and more, then let me zoom out a little bit. When you look at that, does it look like we've got more green or more red? Looks like more green, right? We have more moving away than moving in. And so at that point with this little infinitesimal ball, you've got more of a probability that you're going to be pushed away from that point than you are going to be pulled into it. And so that would be a source, because things want to move away. Okay. Now let me take the number of vectors down so I don't kill my computer here. Let me move the ball around to where maybe we get a negative div. There we go. We've got some negative div over here. So I've moved the point to a different place. And now I'm going to get a bunch of vectors in here. And as I put more and more vectors in, you can kind of see, it's hard, but you can kind of see that there's an overwhelming number of red vectors here. And they overpower the green ones. So my div here is negative. So again, if you were to be a particle in a fluid moving near that point, you have a higher tendency or higher probability of wanting to get pulled into that region as opposed to pushed away. So that would be referred to as a sink. And then what would div equal 0 mean?
It's an equal amount.
Yeah, it's an equal amount. It doesn't mean that there's none going away, none going in. It just means that they're equal. Let me see if I can't move to a place where I have a div that's 0. Oh, I had it right there, div 0. Man, I can't see it. It's hard to see this. I think that's good enough. We've got some going out, some going in, right? But they're equal in the sense there's as much red as there is green. Does that kind of make sense? Now let me show you the same idea with a two-dimensional vector field, because I think with 2 dimensions it's even easier to understand. So if we're in a 2-dimensional vector field, I can show you the vector field without it being too confusing. And then I can actually show you some vectors. So remember, there's an infinitesimal little point here, and we're taking this little tiny circle around it, real infinitesimally small circle, and we're picking some random points on that circle. And at those points, we're looking at how many of the vectors are going into the circle as opposed to away. And can you all see here that there's as much red going in as there is green going out? Now let me slide this to the right and let's see what happens. Okay, so this I think you can see, obviously, I think it's more obvious that the red vectors here, they're all over here, and those vectors are going into the circle. But the green ones, which I can do in blue, are starting here and they're going away. So you have, it looks like you have an equal amount going in and going out at the same time. And you can see that the div is 0, right? And it actually doesn't matter where I move in this vector field. It looks like my div is always 0, right? Let me do a different vector field. Okay, so now I have a negative div. I've got more red than I have green. And as I move this thing around, let's see what happens. We're getting close to div 0. Never quite made it to 0. Getting closer to 0. Oh, there we go. There we go. We have div 0. We have like an equal amount going in and an equal amount coming out. Oh, here we go. There we've got some positive div. You can see it. The vectors are wanting to leave here. I've got more tendency to come out away from this point than in. Okay, that's div. It's a measurement of this, this tendency to be going in towards the point or being pushed away or nothing, or just a net total of nothing. Okay, so this last little part of this note really is just something we'll use later. There's two new versions of Green's theorem. Okay, Green's theorem. Remember, Green's theorem says that if we have some closed curve C, that we can, instead of doing the line integral along that closed curve, we can do the double integral over D. So this turns into double integral over D of partial of Q with respect to X minus partial of P with respect to Y, dA. That's Green's theorem, right? That's Green's theorem. Well, this just says that that's the same as taking the curl of F and dotting it with the K vector. Now, do y'all remember what the K vector is? 0, 0, 1. Right, that's K. Remember IJK, right? I hat, J hat, K hat. That's the K vector. If I take curl, so the curl goes here. Let me go back in my notes and show you what the curl vector is. When I talked about curl, I said there is a formula for it, but it's easier to remember doing a cross product. Here's the formula for curl. I have to clear all this out of here, sorry. Here's the formula for curl, and this is a vector. It has 3 components. See that? And if I dot that with K, 0, 0, 1, do y'all see the only thing that comes out is this times 1? And isn't that partial Q with respect to X minus partial P with respect to Y? Isn't that the formula I gave you for Green's theorem? That is, right? So it's just all this note is just to say, hey, look, by the way, that's another way you can look at Green's theorem. And then there's another version of Green's theorem, which we'll use later on if we get to it. I think we will, which I will explain this when we get to it, okay? Just don't worry about it for right now, but just be aware that there's going to be another formula of Green's theorem that we're going to see in a little while. Okay, now there are a ton of properties of curl and div, relationships that you have. And I'm not going to cover this. I'm not going to test you on it. This is one example from the book. It's an identity that you would be asked to show. So it says, show that if you take the div of the cross product of 2 vector fields, it's the same as doing the vector field G dotted with the curl of F minus the F vector field dotted with the curl of G. So this is like an identity. And then this is the actual work for it, which I'm not going to go through. I just want you to be aware that there are all these different identities that you can prove that show relationships between div and curl. And they're good exercises, but I don't think they're going to be worth our time. So I'm moving on. All right, that's it for that section. And now we're ready to move into 13.6. Okay, so 13.6, parametric surfaces and their areas. This section is, I don't like the way the book does it in the sense that they tell you something and then they expect that you're just like really good with it right away. And I always like to take some time to make sure that students understand this, because if you don't understand it, you can't do anything else after this. So let me first introduce the idea, then we're going to take a step away and we're going to do some practice problems, and then we're going to come back to the section. So parametric surfaces and their areas. Remember from earlier this semester, chapter 10, section 7, we talked about vector functions. And we said that when you take a vector function like r of t, that it could either have 2 components or 3 components. So it's either going to be a 2-dimensional or 3-dimensional curve in the space. So a vector function takes some value of t in, right, like time in the background, and it starts to draw you a curve either in 2-dimensional space or 3-dimensional space. But it is a curve, right? It's not a surface and it's not a solid. It is a curve. Examples that we did, this is an example from way back when. This is an example of this blue curve as a vector function. Here's the actual vector function. As we plug in different values of t, it spits out vectors that create the curve, 2-dimensional. We talked about 3-dimensional vector functions. Remember that spiral we did? There it is right there, cosine t, sine t, t over 5. That's almost the vector function from that problem we did where the man was walking up the silo tower with the paint bucket. That's almost that function. It's a curve in 3-dimensional space. We now look at a new concept. What if the vector function has 2 parameters, u and v, instead of just 1? I mean, what if I create a vector function where instead of you give me t and I spit out a vector, you give me 2 inputs and I spit out a vector. And the 2 inputs that I want you to give me are u and v. So I want you to give me 2 inputs, u and v. I'm going to plug that into a vector function and I'm going to spit out a 3-dimensional vector. Each of the components of that vector function, x component, y component, and z component, will both be functions of 2 variables. As u and v take on different values, the function generates a surface in 3-dimensional space. And those equations in here are referred to as the parametric equations for the surface. So we now are going to explore this idea, because from here, the book just starts getting into like the calculus, okay? They just start getting into the calculus of things. And I don't want to do that. So we're going to step away. I emailed everybody something right before class. And I'll put it in the chat just in case you didn't get it. If you want to follow along, you'll have it. If not, you can just watch what I'm doing here. Wait a minute, where is it? Oh, there it is. Okay, see if that went through. So it's in the chat. It's also in your Canvas email. And what you should be looking at is this right here. This parametric surfaces and their areas handout. We got it?
Yeah, I got it.
Okay, so look, what this is about, this practice sheet is about, I'm going to give us a surface and I want you and I to together come up with the actual function that draws the surface. And it needs to be a vector function, which means it needs to be an R vector function that takes in u and v and spits out some 3-dimensional vector. So we need to figure out what these component functions need to be in order to draw the surfaces I'm talking about, all right? And I think once we get through this, you'll have a better understanding of how this works. All right, so the first one, example A, I'm going to switch to a different view of this so that you can be clear on what it is. Here it is. This is a disk. Okay, this is a disk. The x-axis is the red, the y-axis is the green, and the z-axis is the blue. So for those computer people, y'all may have seen RGB, right? Red, green, blue, RGB. That's like, you look at like monitors, RGB, red, green, blue. No, am I making any sense? Red, green, blue. If you've seen it, you know what I'm talking about. If you haven't, don't worry about it. I'm going red, green, blue. That's X, Y, Z. Okay. So this is a disk that looks like it has a radius of 2, right? And it's all the points inside the disk, right? So this is not a circle. This is a disk. So we want to be able to draw this. All right, so let's try and draw this. Well, what do we know how to draw with vector functions? What can we draw? We can draw curves, right? And so what we need to try and see is if we can imagine that this surface is just a bunch of curves put together. So I think I could imagine that this would be like a circle, and then another circle, then another circle, then another circle, then another circle, then another circle. It's all these circles, right? Now, if this is the X and this is the Z and this is the Y, then how could I draw just one of these circles? What would my component functions need to be? Be careful here.
Cosine of t, 0, sine of t.
Okay, so the Y value, you're saying since this disk is flat onto the XZ plane, you're saying the Y component should always be 0. I totally agree. Does everyone see that? Because it's flat. Y should always be 0. And then you're saying cosine t, sine t for the X and the Z respectively would draw, this would draw a circle of radius 1, wouldn't it?
Yes.
Okay. So if we define it this way right now, I'm just going to write this down. If we did this, it would draw just that circle, right?
Yes.
But see, the thing is, we can control 2 variables. So instead of looking at it like this, I want us to have the freedom to use 2 variables in here instead. So we can leave this 0. We can use 1 variable to control the angle like we were using for the t. So how about we call that cosine u, this one's sine of u. But now we have another variable, v, that we can use anywhere we want. So where would be a good place to put that v?
Let's multiply the cosine and the sine by v.
Yeah.
Or we can multiply the whole scale, the whole function, and use it as a scalar.
You could, because it wouldn't have an impact on 0, right? But the v itself controls the radius, doesn't it, of the circle we're drawing? And so what we're allowing ourselves to do is this: we're gonna set a restriction on u to be between 0 and 2 pi, and then we're gonna set a restriction on v to be the smallest radius I want to draw out to the biggest radius I want to draw. So that should be from 0 to 2. And so the way I like to think about this is that what you're going to do is to draw this surface. Imagine that you let's fix, this is me just thinking through what's happening. I'm going to fix v, okay? Let me fix v. And let's start with v being 0. If v is 0, now let u go between 0 and 2 pi. So v is 0, v is 0. I'm going to get 0, 0, 0, and that draws me the origin, right? It draws me that point. And now I'm going to let v be, I don't know, bigger than 0. So I can go between 0 and 2. So I don't know, maybe I'll go like 1/2, okay? So if v is 1/2, now what is that? And now I let u go between 0 and 2 pi. What's that going to draw me?
Circle radius 1/4.
One half, because this is the radius right here, right? But see, I do this for all v's. See, I do this for all v's between 0 and 2. So I start at 0, draw, move it a little bit, draw, move it a little bit, draw, move it, draw, 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 draw. And when I stop at 2, I wind up getting the whole disk. Does that make sense? Any questions? So the answer is this. That vector function with those restrictions. Okay. That was the easiest problem we're going to do. All right, let's move on to another one now. The next one is this right here. Find the vector functions plural, which yield the four faces of the tetrahedron with these vertices. And I told you what I gave you the equation of this plane. We know from our past experience that if somebody gives us the vertices of something, like we can find out, we can take this point, this point, this point, we can get vectors, cross them, and get the equation of the plane, couldn't we? I've already done that. Here's the equation of that plane. So I've saved to save us some time. There are four surfaces here. Let's call this surface surface 1. Let's see, the back side over here, that's surface 2. This back side here, that's surface 3. And then we have the bottom of this thing, that's surface 4. Four surfaces. We need 4 vector equations to draw each one. All right. So let's start with the easy ones. Surface 4, I think, is the easiest one to draw. Okay. So think about surface 4. If you look at surface 4 from the top, where's my cursor? There it is. Okay. This is the x-axis, so it goes out 4 here. And then it's 4 here on the y-axis. And it's this right here. And we want to draw this surface. And we want to draw it with a vector function. So I'm going to call it R sub 4 because it matches up with surface 4 of UV.
Go out 3 on the
Pardon me?
x-axis. Doesn't it only go out 3 on the x-axis?
Was it 3? Oh
Yeah.
yeah, wait, hold on. Yes, I'm sorry. My mistake. Why did I put 4? I mean, it obviously says 4 right there. Thanks, Greg. Thanks, Greg. Benjamin. Sorry. Yeah, 3 to 4. So we want a vector function which draws this. Okay, that means we need something for each of the components. The easiest component of this is the z. Because it's flat on the ground, I know z must be 0, right? Now, I'm going to let you think about what the x and the y have to be here. The x and the y components. You have 2 variables that you get to control. I hope that everyone is comfortable with the idea that this is the line y equals, let's see, what's the slope of this? Down 4/3, negative 4/3, x plus 4. Right, that's the slope of this line. So that's the relationship we have.
Can I take a shot?
Go for it.
So could I just make the x component u and the y component negative 4/3 v plus 4?
Negative 4/3, what?
V plus 4?
Plus 4. Okay. I'm not going to say no yet, but what would your restriction on u be?
My restriction on u would probably be between 0 and 3.
0 and 3. Okay. So that will draw you things between here and here, right? And then your v is restricted where then?
Actually, I think I want to change it to just be negative 4/3 V and scratch the +4. And then I would restrict it between 0 and 4. It's a shot in the dark.
Okay. Let's think about what we're trying to do here. If you look at this region here, think of it almost like a type 1 region, okay? Like back from we were doing integrals. Here we would say the x's have to be between 0 and 3, right? And the y's would have to be between what? Like if we were doing good old-fashioned type 1 region, x has to be between 0 and 3, right? And the y's would have to be between what?
0 and negative 4/3 x plus 4.
Negative 4/3 x plus 4, right? That's what we would say if it's where type 1 region. So over here, that's pretty much the same thing that we have here. Look, we have, in order to draw this region, my x component needs to be, we'll call it u, and that u has to be between 0 and 3. Now, my y component has to be, well, something else, not u, it's got to be v. But that v must be between 0 and negative 4/3 u plus 4. Okay, so this is probably a little strange looking, because look at the restrictions on v depend on u. So if someone right now were to fix me a u, fix u. So let's let u be 0, okay? If u is 0, then we're right here, right? And now I'm allowed to draw my v. Okay, so no, I should say this. If u is 0, we get 0 here. And then what happens to the v? Well, v would then be between 0 and, replace that u with 0, you get 0 and 4, right? So now my v, which is my y component, would be everything between 0 and 4. So that would give me this line segment right there. If I fix u to be 0, it's going to draw me that line segment right there. Let's fix u to be something else. If u is 1, what would happen? We get 1, so we move out to the right, we're at 1. And now I have to draw everything between 0 and, let's see, if we plug 1 in here, it'd be negative 4/3 plus 4, which would basically be everything from here to here. So I wouldn't draw the whole way up to 4. Do you see that? And what if u is 3?
I mean, v equals 0 there.
Yeah, sorry, 3 would be here. We'd be at 3. And then if we plug in 3 here, the 3's would cancel. We get negative 4 plus 4, and that would give you 0, which means we go out here to 3 and we wouldn't draw up and down at all. So what you're essentially doing is moving your u between 0 and 3, and you keep drawing these little line segments each time you move your u until you draw the whole region. Does that make sense? It's weird because having two variables allows you so much control that it's a little confusing, I think, when you first see it. So here is the surface for, there's the surface for information, and that is the vector function with these constraints that draw surface for. Let's try surface 3. Try and squeeze it onto the same page here. Surface 3 is this back region here, which if I drew it would be the y plane and the z plane, or z axis, sorry. And it looks like we're at 4 here and 2 up here. And so this is our piece right here. We need to draw this thing in here. Now, what is this equation of that line? You have
-2.
y and z, right? So z is, what's the slope of this line?
-2/4.
-2/4 or -1/2 y, and then our y-intercept, or in this case, our z-intercept would be +2. So can't we do kind of like the same thing we did here? Shit, where's my cursor? It keeps going away. There it is. Okay. Can't we do kind of the same thing we did here then? We can create a vector function r sub 3 of uv, sorry, not vector u, of uv, which is going to, all right, which of these is the easy one? If we're on surface 3. Flat up on the YZ plane, right? So
X.
X is 0. Okay. And then because this is like the same problem we just had, I can let this be U and this be V. Restrict my U and my V how? My U should be between what? U is controlling the Y, right?
Between 0 and 4.
0 and 4. Okay. And then the V should be between
0 and -1/2 u plus 2.
U plus 2. There we go. So my U is really my Y because it's in the Y component position, right? It's in the Y component position. So I'm going to move back and forth between 0 and 4 there. That's my U. And then my V is my up and down will be controlled by this inequality. All right, what about this? How about you try S2? I'll give you like 3 minutes. You try and give me S2. Three minutes.
I think I got this.
Go for it.
I got that the slope or the two-dimensional graph for this is z versus x, and it's a slope, or z equals -2/3 x plus 2.
Okay.
And then the equation for the vector of R2 u of v equals u, or the components are u for the x, 0 for the y, and v for the z. bounded between 0 and 3 for u, and between 0 and negative 2/3 u plus 2 for v.
What do y'all think? I agree. Good job. That's it. Okay. Any questions? We're not done. We have one more surface. We did the 3 easiest ones. Now we have to do surface 3. So with surface 3, I gave you the equation of the plane. Please understand again that if I didn't give you that equation, you would have to go find that equation using these points and then somehow creating vectors, crossing them. I already said that, right? But because we have the equation of the plane, we can solve it for z. And then this plane right here is a function of 2 variables, x and y, right? So I think the critical point here to draw this surface is to realize the following. When you're looking at that surface there, what do we call S3? What is it?
S1.
S1. Okay, when we look at S1, do you agree that S1 from the top looks exactly like the first surface we did on the bottom? Wasn't it? Was that S3? No, S4.
S4.
Remember we did S4? Doesn't S1 and S2, don't they look exactly the same from the top? Yes? Which would mean that when we draw it, the part that draws the X part and the part that draws the Y part should be identical to the one that we used to draw surface 4. The only difference is that now we have a vertical component to the surface, a Z, right? That Z is the up and down. So when I go to put my S1 together over here, I'm going to squeeze it right here, S1, I already know that that vector function must look exactly like this one right here. In terms of the X and the Y components must look the same. And I must have the same restrictions in order to draw that. So my U is going to be, or my X components U, my Y components V. My restrictions on U are the same. My restrictions on V are the same. Right, so everything's same except the 0. The Z component is no longer 0. What is it? Well, it needs to be on that plane, doesn't it? So it needs to satisfy the equation of that plane. My damn cursor. It needs to satisfy the equation of this plane, and the equation of this plane is 2 minus 2/3 x minus 1/2 y. But for us, what is the x? For us, what is drawing x for us?
U.
U, and what's drawing y?
V.
V. Okay, so then this is just going to become 2 minus 2/3 x, oh sorry, x, u, and then minus 1/2 v. Oh, there it is. The x and y components are just like this one. So it's trying to draw me this, right? It's trying to draw me this, but as it's drawing that, right, as it tries to draw these little red lines, the z is changing, dictated by this, which is the surface above it, that plane. So it's like I'm trying to draw this line right here. I'm trying to draw one of those lines. As I'm drawing it, I'm having to lift up and go up and across. And that'll take me onto some, you know, like a line on the ground here. Up on the top is now being drawn like this instead, if that makes sense. And you start doing all of those together and you create the whole plane. That's pretty cool, right? I think it's cool. In my program that I use to draw these animations, like to do these for you, I'll show you. I have it over here. Here's the little code that I wrote to draw this. To draw that surface, here it is right here. There is the instructions I gave the computer to draw that. I did what's called a parametric plot. And this is like the vector function. Okay, so I said u, v, u for x, v for y. Here's the surface. I wrote it a slightly different way, but that's the surface part. And then I said restrict u between 0 and 3 and restrict v between 0 and -4/3 u plus 4. And that's what it drew. Okay. And then all the other surfaces, here they are. Those are the ones we just did right here. U, 0, v, here are the restrictions. Okay. I'm just showing that to you just so you can see there are ways in computer programs, software to draw these things. All right, you ready for the next surface? Here it is. I gave you the equation of that cylinder, and I want you to draw it for me. So, is this one surface, two surfaces, three surfaces? How many surfaces we got here?
One.
Just one, right? It's just the cylinder, that's it. Now, I do want us to restrict our y values here. I didn't turn the cylinder enough for you to see this, but this cylinder, if you turn it to the side, it actually starts here at 1 and ends over here at 4. But in the thing that I sent to you, I have that restriction right here for you. Okay. How can we draw this? Well, I can do this by drawing a circle, right? I can draw a circle. And then I can draw another circle, and then another circle, and another circle, and another circle, and another circle. All of those circles have the same what?
Radius.
Radius. The only thing that's changing is you're going to slide that circle back and forth, right? So let's see if we can do that.
So wouldn't this be very similar to the first problem?
Kind of, but it's similar. But remember in the first problem, we drew a disk, right?
Mhm.
So what we changed was the radius of the circle. We allowed the radius to grow and shrink, right?
Mhm.
Here, we're going to fix the radius and we're going to slide it back and forth.
Mhm.
Does that make sense?
Yes.
Okay.
So in that case, could I solve?
Yeah, go for it.
I got cosine of u, comma v, comma sine of u, and I bounded u between 0 and 2 pi and v between 0 and 4. Sorry,
Okay,
1 and
so
4. 1 and 4.
What's your x-axis? You could be right depending on how you're looking at this. Is your x-axis the green or the red?
My x-axis is the red because RGB.
Okay, so you said you want your x to be cosine of what?
U.
Okay. And your y component to be what?
V.
Okay. And your z component to be?
Sine of u.
Sine of u. Okay. What do you want your restriction on u to be?
0 and 2 pi.
Okay. And what do you want your restriction on v to be?
1 and 4.
1 to 4. What do y'all think? It's going to work?
I mean, I thought the same thing.
Yeah, this is going to work. Okay, so let's see. Let's make sure we understand. If we looked at this thing from this direction, then we have the x-axis is here and the z-axis is here. So we want to be drawing circles in the xz plane, so to speak. So that means your sine and your cosine are going to need to be, or your cosine and your sine are going to need to be on the x and the z respectively. And then we put a 1 in front because the radius of this is 1. And the reason we know it's 1 is because of the equation I gave you, right? The radius of this is 1. So that should draw me, this and this together should draw me all the circle, a circle of radius 1. And then all we're going to do is vary the y which we're calling V, we're going to just let it slide back and forth between 1 and 4. There we go. That should do it. Good. We move on. Are there any questions on that? I'm going to give you a moment. I'm going to give you 2.5 minutes. Read the instructions. I'm hoping maybe somebody who hasn't responded yet will be willing to take a shot at this.
Sorry, I'm not responding, but did you mean to put end caps or end cap? Just one of them or
Just
both?
one of them, just this red end cap. That's all I want.
Oh, okay.
So this problem is very similar to the first one. Go ahead, Margie.
So you're basically fixing your Z. Your Z is, instead of being fixed at 0, though, it's going to be, oh, is that Y? Is it green? The Y?
Yeah, the Y. So you're fixing your Y at 4.
The Y at 4.
Yeah. Okay, I'll do that. So what about, how do you draw the rest of this? This should just be like a disk, right, Margie?
That's correct. Yeah, you're just really drawing just the disk part of it.
Yeah. Which we did on the first example, didn't we?
You did.
So we want to use cosine and sine.
Right. So
but
your
go ahead.
so your cosine is going to be it's going to be your function of x.
Okay. So I'm going to go cosine of what?
Cosine of u.
Okay. And then over here we'll have sine of u. That
Correct.
will draw me circles, but the problem right now is that all these circles are going to be just a radius of 1. And I want all the circles. Right?
Right.
So you can control those circles by controlling the scalar in front of these trig functions with another variable, like v.
Like -2.
No, we want to be able to control it, right? We want to be able to vary it. So we'll just call it v.
Right. So you're just going to put the v in. Oh, I see. You put the v in front.
That's right.
And that's how you can scale it back and forth.
That's right. Now the u is just going to be our angle restriction, which is going to go 0 to 2 pi to draw the circle. And now the v, if we want to draw the whole disk, is going to start at the origin, or not the origin, at the y-axis at 0 radius and go all the way out to what's the maximum radius we want here.
The maximum radius is going to be, well, the function is 1, but the radius is going to be 4, correct?
Well, the disk is controlled by the cylinder, isn't it?
Mm-hmm.
And so the cylinder has a radius of 1.
Oh, okay. So that is going to be your limit then.
Yeah, so
V.
1 on the v. And that should do it. Okay, we good? I move on. Three surfaces here. Let me show it to you on my computer program first. Okay, there it is. Did y'all get a good look at that? All right, here we go. Let's label these first. S1, S2, S3. Let's start with S1 because it's the easiest one. The S1 is this back disk, isn't it? That back disk. And that back disk is drawn in the XZ plane. And it's just like what Margie just did, because it has a radius of 1. But the Y is fixed at 0 instead of 4. So this should be pretty straightforward. Let's see, R of U V equals, let's see, V cosine U. The Y is fixed at 0, and then V sine U. And then U is between 0 and 2 pi. And the V will be between 0 and 1. Oh, we got the first one. We good there? Okay, S2. S2 is a fun one. So for S2, think about what's happening on S2. S2 is this like bluish outer shell of the cylinder. If you look at it from here, it's always just drawing a circle, right? Trying to draw a circle. But instead of drawing circles and sliding them back and forth like we did for this problem, right? This was just draw the same circle over and over and just slide the Y back and forth between 1 and 4. Here, we want to kind of draw the circles, but we don't want our Y to go between 1 and 4 anymore, do we? Our Y has to be between, what do our Y's always have to be between? So if I were to pick some point here on that circle, I want my Y value to be stuck between here and here. And then if I picked another point on that circle, I want my Y value to be stuck between here and here, or here, here to here, here to here, right? So aren't my Y values always stuck between the back surface, which is Y equals 0, and the front surface, which is the plane, right? All right, let's see if we can't put that all together in our notes here. So for S2, first, I'm going to draw the cylinder itself, the circles, and they all have a radius of 1. And it's the X and it's the Z that are drawing me the circles. Right? So the X is always going to be cosine of U, the Z is going to be sine of U. That should draw me circles in the XZ plane. But now I want the Y to always go back and forth between something. Okay, how the hell do I do this then? What do I put in the middle here? What do I put?
I have a quick question.
Yeah.
So should we scale cosine and sine by V since we're kind of doing it in relation to the disk in the back? Since we're using the disk in the back as a reference?
Well, we're not using the disk in the back as a reference because this blue shell that we're drawing, come on cursor, where are you? This blue shell is never inside. It's not solid. This is the outer surface only that we're drawing.
Okay.
Right? So parametric functions of two variables can only draw surfaces. They can't draw solids.
Okay,
You would actually need a parametric function of 3 variables to draw a solid. But we only study up to 2.
boring.
Yeah. Okay, so do you all agree that this cosine u sine u will always draw me circle? So I will always land on the outer boundary of this cylinder, right? It's the back and forth I need to control now. So how do I control that? What do I do here? What's going on?
Can I attempt
Yeah, go
to?
ahead. Yeah, anybody.
So I'm thinking my y component is going to be v. And then we're going to have to bound v between 0 and some function of cosine and sine, maybe.
Okay. So you want me to put v here,
Yes,
and that v, you want me to bound that between, you said 0, because
Mhm.
that would be this backside, right?
Mhm.
This is y equals 0, right? That's y equals 0. So I'm going to bound it at 0. And then what about this bound over here? Every point on the edge here is also on that plane, isn't it?
Yeah, I was thinking we should rearrange it to be in terms of y is in terms of x, z, and 2. And then our x and z component, x and z, well, we just switched them out with our x and z component. So sine of u and cosine of u.
Exactly, exactly. So because the outer edge of this, which is my y, which is my upper bound on my y control here, is part of this plane. If I solve this for y, I'm solving it for y because the y is the v, then I need that to be between 0 and this plane, 2 minus, but I can't put x because we don't have x anymore, but what's x for us? Cosine u,
Yeah,
right? And then plus, and then z, but what's z for us? Sine of u. Does that make sense? See, the book doesn't do this. They don't go through and start doing examples so you can get a grasp on this before you actually do the calculus. Now, if you don't believe that that draws it, here's my code, and it's this first one here: cosine u, v, sine u, u is between 0 and 2 pi, v is between 0 and 2 minus cosine u plus sine u, right there. And that's going to draw me the blue one, the blue region here. So that's the blue one right there. Or the blue surface. Okay. 2 down, 1 to go. Okay, S3, this right here. So for S3, if you look at S3 from the front like this, isn't that the same as that back disk? In the terms of the XZ plane, isn't it still just like a disk? With the only thing changing is the in and out towards you and away from you. So I know how to draw the disk, right? Didn't Margie do that for us earlier? We drew the disk here. So to do S3, I'm going to kind of steal the information from here. And I'm going to draw the disk in the XZ plane. That's this. But see, now my y is no longer flat. What does my y have to be?
I have a feeling that it should be similar to the boundary that we used for S2.
Yeah, exactly. Now, we have to be careful on one thing here.
But it should have the V's in front of the cosine and sine, I think.
Yeah, our limits of integration, our restrictions on u and v here, our restrictions cannot change. If we're still going to draw that disk in the xz plane, we still have to stick with these limits on u and v, which means that this right here can't just be v. It has to be, where exactly will you be? Like, what point do you want to be at? You want to be somewhere on the surface, right? On it. You want to be on that surface. So you've got to solve that equation for y again, 2 minus x plus z, but x is no longer cosine u like it was in surface 2. It's actually v cosine u. Sorry, that's not, I forgot the minus. And then plus v sine u. So this draws me the disk, not the circle, the disk. And this part guarantees that as I draw the disk, the y coordinate is always landing on the plane. You having fun yet?
Yes.
Mhm. All right, I think I have one more. No, we have two more. Okay, so we have 4 surfaces here. Let's take 10 minutes. Okay, I'm going to give you 10 minutes to see if you can come up with all 4 surfaces. Does anyone need me to spin this around or show you anything here? This is 1 here. On the back side, it's -1. These points come out to 2 here. I'll show it to you on the 3-dimensional one that I can move around. So it is flat in the back, it's flat on the bottom. 1 and -1 there, and then on the top, you can see it's 0 to 2. And I'm going to label them. I'm going to label the surfaces. That way we're all consistent. I'm sorry if you've already started doing that. I'll go S1 here. I'll call this one S2. Those are the easiest ones. Then S3 and S4. Okay. 9 minutes. I am skipping the previous example, example F. I'll leave that for you for fun. Okay. Okay, I think that's about enough time, as much time as we can take on this. All right, so who wants to give me the vector function for surface 1?
Would it be u0v? We bound u between -1 and +1, and we bound v between 0 and 1 minus u squared.
Okay, so you said u between where?
-1 and +1.
And v between where?
0 and 1 minus u squared.
Does anybody disagree?
No, that's what I put.
Yep, that looks good to me. Okay, that looks good to me. Any questions on why that's that? Okay, good. How about it? How about the surface 2? What's the vector function for surface 2?
That one was, I put uv0 with u bounded between 1 and -1 and v bounded between 0 and 2.
Yeah, that's just drawing just a real basic rectangle on the ground, right? Okay, what about S3? S3 is a little weird.
I took a shot at it and went with uv 1 minus u squared.
U, V, 1 minus U squared. And then your restrictions on U,
-1 and 1.
okay, on V,
0 and 2 minus u.
okay. Let's think about this. So we want to draw this blue surface. Come on. Where is it? Okay, we want to draw this blue surface. So we know that the x's will have to be between -1 and 1. So I like that. U is between -1 and 1. The v is the y coordinate. The y coordinate has to go back and forth, and it always has to be between y is 0, which is the back edge, and then this surface, which is this. And if we solve this for y, we get 2 minus z, right? So, yes?
Yeah.
Okay. So our v here would be between 0 and 2 minus u. Where are you getting the u from? Maybe let's do it this way. Let's look at the z component. The z is this blue shell that goes up and down, right? That has to be dictated by this, right? And so that is 1 minus x squared, but we know the x is 1 minus u. Sorry, the x is u. So this will be 1 minus u squared. That'll keep us up here. Yeah?
So would I then make v between 0 and 3 minus u squared?
Yeah, we have to take this and solve it for, well, we're trying to control the y, right? So y is 2 minus z. And z for us will be 1 minus u squared, right? So this should be 2 minus 1 minus u squared, which will become 1 plus u squared. Let me just double check mine. Yeah, that's it. Does that make sense, Benjamin?
Yeah, it does.
Okay, good. Does anyone else have a question on that one? That one's tricky. How about the fourth one, the surface here? So I can do the same thing. The x's will be between -1 and 1. It's pretty much S1, isn't it? It's the same as S1, except I need to control the back and forth with this one. So S1 was this one, so I have to stick with U, V. I have to stick with -1 to 1 for U, and V has to be between 0 and 1 minus U squared. Is that right? That should draw me the back surface. Now I need to bring it out to here. So I need that my y value is 2 minus z. So for us, that's 2 minus z, but z for us is v. That's it. Okay, we've got to move on. I hope that this gives you some idea of how you can use parametric functions or vector functions of two variables in order to draw surfaces in three-dimensional space. Now, why do we want to be able to do that? We want to be able to do that because, you know what? Yeah, I'll get back to that one. You know what? Hold on a second. Let me go. I'm gonna just give you one more example. Okay, one more example. This one, I'm not giving you the picture and asking you for the vector function. I'm actually giving you the vector function and asking you if you recognize this. So we have r of uv is sine u cosine v, sine u sine v, cosine u. And initially, and then I'm also going to restrict the u between 0 and pi and the v between 0 and 2 pi. So you may or may not recognize this. If I replace my v's with thetas, and I replace my u's with phi, then you might recognize that as our spherical coordinate conversion. Remember, x was equal to rho cosine theta sine phi. Y was equal to rho sine theta sine phi, and then z was equal to rho cosine phi. Do you all remember that for spherical? If rho is 1, then we have this. So this should draw us the unit sphere, which it does. I can show you here. The way it does it is that as we change u, we start moving up and down the sphere. As we change v, we start wrapping around. And if you put all those together, right, you draw the whole sphere, all the different combinations. Okay. So that's an example of a vector function of two variables that draws a surface that is somewhat familiar to us from the past. Now that we have established that we can draw vector functions, or we can draw surfaces with vector functions, we want to remember back when we were doing this in 10.7 that when you were given a vector function, we could take the derivative of it, and it gave us a vector that was tangent to our curve, right, at any point. Well, here's a picture of that. Okay. Now what we have is a vector function that draws a surface. And so we would, if we fix one of the variables, hold it, then we'll be drawing one of the curves. Or if we fix the other variable, we'll be drawing another curve, a different direction. Each one of those curves individually has its own tangent vector, as you can see from this picture. You see the two tangent vectors? And those two tangent vectors we can find by, again, holding something constant. That's a partial derivative. So when you have a vector function of two variables, we will now write r subscript u to mean the tangent vector to that surface where we're holding v constant. So it's the partial of r with respect to u, hold v constant. This would be the partial of r with respect to v, which means you're going to hold the u constant. Those two different calculations will give us two vectors, and those vectors will represent these tangent vectors. So y'all know where I'm going with this? we have two vectors that are tangent to our surface. If I have two vectors that are tangent to a surface, then I can cross them and get a normal, can't I? And that should give me a plane. So there is a plane, right? There is a plane that these two vectors live on, and that plane would run tangent to our surface at that point. And that's what the next thing is about, the tangent plane to a parametric surface. So if we're given a surface with the vector equation, we can find the equation of the tangent plane at any point on the surface. So we will be able to find the equation of that plane, but it will require a calculation. So what do you think we're going to have to do to find the equation of a plane at a point? Calculate the partial? Calculate the partial? Cross them? Yeah? Okay. We're going to do an example here. I don't know if I want to do that example. Yeah, let's do it. Find the equation of the plane tangent to the unit sphere at this point. Got 9 minutes. Okay, I need that. And I need, how do we draw a sphere? This is how we draw a sphere, right? Or that's how we draw the unit sphere, I should say. So if we're going to find the equation of a tangent plane, then we know that the equation of the tangent plane will be a x minus x naught plus b, right? Y minus y naught plus c, z minus z naught equals 0. The only thing we have to figure out is the normal vector, which is the vector ABC, right? We just have to figure out that because we already know x naught, y naught, z naught is given to us in the problem. So to figure that normal out, what we're going to do is we're going to take the partial of our surface function with respect to u and cross it with the partial with respect to v. If we can cross those two vectors, those two tangent vectors together, we'll get our normal vector. So let's look at the partials. What is the partial of r with respect to u? Okay, it's going to be a vector. So I've got to take the partial of this with respect to u. We're going to do this component by component. So the partial with respect to u would be, let's see, cosine u, cosine v, and then derivative of this, which would be cosine u, sine v, and then cosine of u, derivative of that, which would be negative sine of u. Okay, now I need the partial of this with respect to v, which now is going to give me negative sine u, sine v. And then when I do the partial of this with respect to v, I get sine u, cosine v. Stop me if you have a question. What's the partial of this with respect to v?
0.
0. That's nice. And now I need to cross these. So I'm going to save myself time. This is where we do like I, J, K. And then we do that little like cover up the I and then do the little determinant over here. So R U crossed with R V will be equal to, okay, the I part of this will be this times 0, which is 0, minus this times this, which is going to be negative sine squared u cosine v. Sorry, plus. Right, it's plus because I'm subtracting this, but it's negative. I apologize. All right, now we cover up the middle one, and we do this times this, which is 0, minus this times this, which would be a negative, but then we have to change the sign, so it would be positive. Sine squared u sine v. And then we do the last part, which we cover up the k part, and we do this here, here, minus this. So that's going to give us, it's cosine u, sine u, cosine squared v, minus, let me make sure I got that right. Yeah, minus, but then that's going to be plus because there's already a minus there. And then it looks like we're going to have cosine u, sine u, sine squared v. There it is. Now, we need to figure out what the value of this cross product is, right? To figure out what A, B, and C are, we need to now go to the point that we're talking about. So let's look at our point. Here's our point, right? We have to figure out what U and what V give us this point. And then we can plug that in here, and that will give us our normal vector. So what U gives us this and what V. I think the easiest part to look at here is probably this. Let's see, when would cosine of U be 0? I'm sorry, not 0, root 2 over 2. So where's cosine something?
Pi over 4.
At pi over 4, right? And pi over 4 is in here. So it looks like U would need to be pi over 4. Okay, how about right here? How about this middle one, 0? How can we make this 0? We can't control U anymore. U is pi over 4. So sine of pi over 4, that's root 2 over 2, but that would have to be 0, right? So where would sine of V be 0?
At a pi or 0?
At pi or 0? Y'all agree?
Just go with 0 though.
Go with 0? Well, it's either V is equal to pi or V is equal to 0, right? Maybe we can tell by the first one. Look at the first one. We need this first one to be root 2 over 2 also. So sine of U, we know U is pi over 4, so that's root 2 over 2, right? And we need this then to be 1.
So
So
0.
that's 0.
So that means it would have to be the V 0. Does that make sense? So now that we have that, we can plug that in. We know U is pi over 4, V is 0. Now let's go and figure out what this is.
Can we simplify the Z coordinate a little bit?
Yeah, we put them together, right? Because they're the same.
Well, you can take out the cosine.
Oh, you can take out the, yeah, you can take out the cosine. Yeah, so this at the end becomes 2 cosine U sine U. Yeah, right? You can factor out a.
No, just
Oh,
because.
no, just one of them. Sorry.
Because then the other one just
Factor it out. Okay, so let's try this. Let's let V be 0 and this. Okay, so what happens here? Sine squared of U, so pi over 4 is U. So sine of pi over 4 is root 2 over 2, then we square it. What's root 2 over 2 squared?
1/4.
1/2, right? You square the root 2, you get 2, square that, you get 4, you get 2 over 4, it's 1/2, right? Times cosine of 0 is 1, comma. Okay, now how about here? This one's going to be easy. I think it's easy. What's sine of V? What's sine of 0?
0.
0. Okay, so that's 0. And then over here, let's see, cosine of U. All right, cosine of U, U is pi over 4, so that's root 2 over 2 times sine of U, which is also root 2 over 2. And so it looks like we're getting 1/2, 0, 1/2 again. There's our normal vector. So now we can come up with the equation. It's 1/2 x minus x naught was √2/2. And then plus 0, y minus 0, that doesn't really even matter. And then we have plus 1/2 z minus √2/2 equals 0. There it is. That's the equation of the plane. So that means that if we were to go and try and go to that point, let me see if I have it drawn. We are going to try and find the equation of this plane here. Let's see if I'm at the pi/4 and z is at 0. Yeah. Okay, so there it is. That's the plane right there. We just found the equation of that. Let me see, because we're out of time. Let me see. Do I actually have that answer in here anywhere? No, it doesn't look like I do. Yeah, it's just drawing a polygon. Let me see, show answer. There's the plane. Let me see where show answer is. Show answer, true, false, show answer, show answer, show answer. Here we go, contour plot. It was 1/2 x minus the square root of 2/2 plus 1/2 z minus square root of 2/2 equals 0, right? That was it?
Yeah.
Yeah, so okay, I did have it in there. Okay, yeah, so that just verifies that we got it. The cool thing is you can do that for any surface now, right? You're going to find the equation of the tangent plane at any point. You just have to take the two partials, cross them. That'll give you your normal vector. You plug in the point or figure out the u and v that give you that point, and then you're off to the races. Okay, we are out of time, unfortunately. What else do we have in here? Surface areas. So ultimately, where we're going next week is that now that we know how to do this, we're going to be able to find the surface area of any surface. So we're going to use double integrals to do surface areas. So we'll find the surface area of the sphere, and then after we do surface areas, we move on to now putting our surface in a vector field. And so you have a surface in a vector field, and you're trying to measure how much of the vector field is going through your surface. And that's what's called flux in physics. I just don't know how far we're going to get. Okay, everyone, have a good weekend. Oh, your mini exam, the mini exam 6, if you're going to turn it in, let's say it's due on Friday by noon. The only thing we were missing was the idea of incompressible, but I did that today. Divergence is 0, means you're incompressible. And I'm going to try and throw one more mini exam out in the next day or two. Just one final one. And you all have the review I sent, right? With all the problems, like 24 problems. And you understand that your final exam is going to come from those problems, right? I did say that to you. I'm not going to tell you which ones. And I will offer help, but I'm not going to go through and give you the correct answers to, all the problems. If you meet with me, I can talk to you about whether or not you're on the right track. Everything looks pretty good, but I'm not going to verify like thumbs up or down whether or not you have the right answer.
I had a question.
Yep.
Is
You're
our
pretty good.
final gonna be take home like the mini exams have been, or are we gonna have to join class and do it in?
You're going to join class and do it. That was kind of the whole idea, was that I would give you basically, like, you have your final exam in your hands right now. You just don't know which problems they are.
Will it be like identical problems? Like you're gonna grab question 2 straight from the review, not change any of the numbers? Or are you going to change up the numbers, maybe change it slightly?
I said that it would be identical,
Okay,
which is why it's going to be very important for you to be on camera and for me to verify that the only things in front of you are blank pages and your formula sheets. That's going to be a critical part of us getting ready for the exam. And because you will have, in theory, you will have worked all the problems out and have them all worked out. And I just don't want you sitting there flipping through your own work, writing down what you wrote. I want it to be up here.
and do we know the day of the final? I guess that's my last question for now.
Yeah, we do. I haven't looked at it. Let me see if I still have the schedule. Let me see. It's Wednesday, May 12th. So next Wednesday, no, not next Wednesday, 2 Wednesdays from today,
Literally 2 weeks.
2 weeks from today, but our exam actually starts at 12:30, not at 1. And that's not my doing, that's the college. So I will come in here at 12:30. I'll probably be in here at like 12:15. If you want to come in here and get set up early, we can. And then what I'm going to do, just so everyone knows, what I'm going to do is we're not going to take any time for you to write the problems down. Okay. What I want you to make sure is that you have a copy of the problems I sent you, have it printed out with nothing written on it. And that way, when it comes to the day of the test, I'm just say, okay, do problems, blah, 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 blah. And then we don't have to take time with you like writing down the problems. You will have it. We can just start immediately and you'll have the full time.
We're gonna like turn it into a Dropbox right after class.
Yeah,
Or at the
right
end.
after class, you'll submit the work. And it's gonna be weird. I'm gonna have to verify that what you're turning in is what you did in front of me and not what you wrote like before class. So I'm gonna have you, when you finish your exam, each one of you is gonna have to put something on your exam that I'm gonna tell you to put on there and then show it to the camera. And that way I know that's the page that you turned in. Does that make sense? Like I'm gonna ask you to write down, I love math or something, and then show it. And that way when I see it, I know that that's what was in front of you, not some work that you did at another time. So there's pros and cons to doing it this way. Just expect to come and do honest work and everything will be fine.
I think it's mostly pro.
Yeah.
How many questions was it going to be out of the thing?
I don't know yet. I'm guessing like maybe 8. You know, you have of the review that I gave you. Let me bring it up. I know class is over already, but let me try and find this review.
Oh, it's the 24 questions.
Yeah, but what I wanted to see was how much of this have we done? Because right now we can't do all of this review because I don't know how far we're going to get. So look, this problem right here, we can do this now, number 17. Find the parametric representations for the 3 surfaces. That's what we did. But then I say next find the unit normal vectors. So that we haven't done. We haven't done 18. We haven't done 19 or 20. So pretty much anything after 17, was it? Anything after 17, we haven't done. So it'll be interesting to see next week how much we get through. I know we'll get through this. And I'm pretty hopeful we'll get through this. I don't know. See, some of these are the same type of problems. What I did is I had multiple final exams I've had from the past. I kind of threw problems in. So some of them are the same. Like this is the same as number 21. Same idea. So hopefully we'll get through the material through 21. Did I do 21 twice? I did do 21 twice, didn't I? I guess there's 25 problems. 22. So 22 and 23 and look, 24, we can just throw that away. I'm not gonna test you on that. Because this was an application from way earlier that we never even went into. We did masses of non-homogeneous laminas, but we didn't do masses of 3-dimensional things. I told you you could, but we never did any problems. So I would say that's not going to be there. These last 2 problems, that one and this one, they look terrible, but they're actually really easy problems, like almost laughably easy. But if you don't know how to do them, then it's not going to be laughably easy. So that's if we get to the end of the semester, if we get to the end of the book, sorry, the last chapter on divergence theorem, then those two will be easy to do. If we don't get to divergence theorem, we just won't have those on the test. All right. So stay tuned. Next week's going to be important. We're going to be sprinting to the finish line. Anything else?
So what I'm hearing is if we get to divergence theory, expect question 20